homework and turn it in on Wednesday. There will be a few miscellaneous loose threads we have to pick up. Ethers, thiols, just mention, let you know what they are. Ethers, you'll have to know another reaction there. But I don't think you need it for it to complete your homework. So it'll take 30, 40 minutes on Wednesday to do that, and there'll be some extra time to review. The exam is next Monday. Chapters 10, 11, and 12. So your Chapter 12 homework, you could probably pick up Monday morning, that sort of thing. See if there's anything there you need to learn about. All right, so that's kind of what we're going to try to accomplish today and Wednesday. Okay, here's where we left off. To warm up here, I don't know if I can do this. No, I can't. Let's make this bigger. Hopefully you can see it. Take a look at these. Let's go. There's 5 of them here from left to right. Let's figure out what each of these is. Is it a primary, secondary, or tertiary alcohol? So here, it's not very big, but I'm having a hard time expanding my screen. Can you see where that OH is? Where is that OH? Where? Well, 1, 2, 3.
Oh, third.
It's actually on the first. Okay? It's on the first carbon. Which makes it a what? Primary. It has only one carbon attached to the carbon that has the OH on it. That's what makes it primary. The second one. This one? Well, both of those are the same thing. They're the same thing. Above it, you have a kind of a hybrid structural formula, and below it, you have a line formula. Say that again? Secondary. Yeah, you're right. No, I look just like the way you pronounced it. That's all. Secondary.
That's what I said.
2 carbons attached to it. So that's secondary. Third one.
Secondary.
Okay, secondary. Again, there is a carbon over here and there is a carbon over here. Just so you see what carbons are we counting. We're not counting the carbon that contains the OH. We're counting the carbons that are attached to that carbon. There's 2 of them. So this is a secondary alcohol. Fourth one. Leah?
Tertiary, right?
No. And I know you're saying it with a little hesitation. Here's the carbon. So we got this carbon here, but there's only one carbon attached to it. We don't. We just count the carbons directly attached to the carbon that has the OH.
So okay.
Okay.
There was one like on the other side, and it would be 3.
Right. If there had been an OH right here, yeah, it would end up in a tertiary carbon. It looks like a tertiary kind of a structure, but it's hanging out here on the end. So OH is out here on the end. It only has one carbon attached to that carbon. And it would be a good idea to come back and examine these by Pretend you don't have the structure, you just have the line. Or just pretend you don't have the line, you just have the structure. So you can identify it either way. So this is a primary alcohol. And then the last one. Okay, that is tertiary. We've got a carbon there, we've got a carbon there, and we've got another one there. So we're just talking about what's directly attached to that carbon. Doesn't matter how long the chain is after that, just what's around it. And what you'll see with these, generally speaking, I mean, this is kind of generally what you see. This is a primary. And you can see there are 2 hydrogens on there. This is a secondary. There's only 1 hydrogen. And this is a tertiary. I'm talking about what's on this carbon that carries the OH. When you got an OH, that's 1 bond, and you have 3 carbons, that's it. That's all you can have. Carbon has 4 bonds around it. So there's no hydrogen on there. This will have some significance when we start talking about reactions. All right, and if you had 2 carbons on there, I suppose I could call these carbons so that you could see. If you have 2 carbons on there, you do have room for a hydrogen. And if you have only 1 carbon on there, you have room for 2 hydrogens. So that's primary, this is secondary, and this is tertiary. Okay. What we're going to look at today, let me just summarize the reactions we're going to look at. We're going to look at how to prepare and the first reaction is going to be one you already know, hydration of an alkene. The second one is going to be the hydrogenation of a carbon-oxygen double bond. That's preparation. And then we're going to look at the reactions of alcohols. Okay, so I'm distinguishing between how to make them and then how do they react. And so today we'll look at the oxidation of alcohols, and we will look at the dehydration of alcohols. All right? And let me just make sure that we know, I'm talking about alkenes. Enes. All right, you got that? All right, the very first one, the hydration, that's when you're reacting water with something. The hydration of an alkene is a reaction you know because in chapter 11, the homework you just got back, or the homework you just got back, you dealt with this reaction. How do you hydrate the hydration of a double bond? And the major product is determined by applying Markovnikov's rule. This is all review. The hydrogen on the water goes to the carbon with the most hydrogen. So a hydrogen goes here, and the rest of the molecule, the OH, the rest of the water molecule, goes on the other carbon. And so in this case, the major product is the isopropyl alcohol, and the minor product is the 1-propanol. It's your minor product. Do you get some of this? Yes. But you get 85 to 90% that. Okay? That's a reaction you already know. Just shake your heads yes, whether you know it or not. Because you should. All right? So now let's go on to a new reaction. So this is one way to prepare alcohols. Here is another way to prepare alcohols. You're familiar with the word hydrogenation. That means you react hydrogen with something. And let's take a peek at that. Let's compare what you do already know. This is really a good, this is what we try to do. When you try to learn something new, it's nice to have your foot on something you already know. You work from what you know and you move to the new thing, right? So what do you know about hydrogenation? This is what you know. Hydrogenation. You know that you can add hydrogen like this, you get a bond there. These electrons moved on into there, you get a bond there. And your hydrogen, one hydrogen goes on each of the carbons that was involved in the double bond to begin with. Yes? Right? Okay, now look at how familiar or how similar this is going to be here. We've got this situation. We are going to hydrogenate a carbon-oxygen double bond. And what is going to happen? Well, pretty much the same thing. We're going to get a different product, but these two electrons are going to go up into there. And the one hydrogen is going on the oxygen. The other hydrogen is going onto the carbon. And what do we get? We get a hydrogen down here. Let me write this a little smaller over here. We get that's an oxygen up there. Sorry. We get that. There's where our two hydrogens went. And we could just write this as an OH, like that. And what is that? It's an alcohol, isn't it? It's another way to prepare an alcohol. And if you're asking the question, well, what is that? That's chapter 13. Okay, we haven't gotten there yet. That is an aldehyde. You're going to hear me talking about aldehydes and ketones today because of they're on the other side of alcohols, just like alkenes are on the other side of it. So one way to prepare alcohols is from alkenes. Another way to prepare alcohols is from aldehydes and ketones. So we won't get worried about naming them, but we'll just kind of worry about generally what are these things, and then they're relevant to alcohols because they're a route for making alcohols. And what this slide is trying to show you right here is that this is an aldehyde and this is a ketone. They both have a carbon-oxygen double bond. Carbon-oxygen double bond, carbon-oxygen double bond. That's why that is what chapter 13 is all about, aldehydes and ketones. What is different? Well, the aldehyde has the carbon-oxygen double bond on the end. You can see a hydrogen there with it. There's only one carbon. So it's always on the end. Carbon-oxygen double bond on the end, aldehyde. Carbon-oxygen double bond. Here it is smack dab in the middle of the molecule, but anywhere along the chain. If it's not on the end, it's a ketone. Okay? So there are only two kinds of carbon-oxygen double bonds. Aldehyde bonds on the end and ketone not on the end. Now the reaction proceeds, the hydrogenation proceeds exactly the same way, but if the carbon-oxygen double bond starts out on the end, the OH ends up on the end. As a consequence, the oxygen does not move. Whatever carbon it started out on is the carbon it ends up on. Keep that in mind, because I have students draw me molecules and they give me an alcohol, it produced an alcohol, but they moved the oxygen. It's not where it started out. All right, so it's the wrong molecule. Keep the oxygen right where it started out, and so the OH ends up on the end, which means it's a primary alcohol. Carbon-oxygen double bond along the chain somewhere, two carbons, a carbon on either side of it. Then you're going to end up with an OH with a carbon on either side of it, which is by definition a secondary alcohol. Okay, that's hydrogenation. And these catalysts, same catalysts you would use to hydrogenate an alkene. Platinum, palladium, nickel, same catalysts. Any one of those. So don't think they're saying you need all three of these things. You need either a platinum, a palladium, or a nickel catalyst to undergo this hydrogenation. Let's see, I'm trying to think if I could give you an example here. Complete these reactions. I'll give you two of them. Top one's an aldehyde, the bottom one is a ketone. Hydrogens around there. That's right.
Okay.
How you doing? Good. Christian, sorry, I saw your email. I'm sorry I saw it this morning.
Oh, it's fine. It's good. It's a big deal.
Yeah, I'll get them up there right after this class.
Okay.
I'll get them both up there. Today's and that one. Okay. All right, on the first one, on the top one, you should have something like this. You're going to get an OH here. You're going to get the other hydrogen there, and then the hydrogen that always was there. And then this will produce a primary alcohol. And the second one would be something like this. You got a methyl group down here. Right here, where that OH, where that oxygen was, here's your hydrogen. This is the hydrogenation. And then, of course, on the other side of it here, we've got another methyl. So this produces a secondary alcohol. I mean, there's all kinds of questions, could ask about this. Here's a reaction, what class of alcohol would be produced? Here's a reaction, draw the structure. Here's a reaction, draw the structure, and name the product. Lots of different questions could be asked here. Don't worry about the names of these. We'll get that after exam 1. We'll come back to chapter 13 and figure out, okay, how do you name aldehydes? And ketones.
Why wouldn't it just be H2O? Like, why wouldn't you just put both of the hydrogens together and then connect it with the oxygen?
Where do you want the H2? Right here? Mm-hmm. Yeah, I mean, you could draw that way. This could be a CH2OH group right there. Is that what you mean?
No,
Let me see what you.
So here I put H2O, then I didn't have a hydrogen there, and then I just had the hydrogen that was already there before it reacted with H2O.
Well, what would you have? H2O.
Mm-hmm, because this is 2 H's, right? And then
So you could OH with a 2 after it? Mm-hmm. Yeah, no, that would, let me show you. That would be something like this. See, that would be something like this, which that would have oxygen with 3 bonds around it.
Okay.
And that doesn't happen. That other H has to come down here. Okay? The hydrogens add across the double bond. One goes to the oxygen, one goes to the carbon.
Okay.
And it's the same way that happens with hydrogenation. One goes to each of the carbons that made up the double bond. They both don't go to the same carbon. They divide up, one to each of those atoms. Okay. Okay, now let's dive into oxidation. So we've gone through how to prepare it. Hydration of a double bond, carbon-carbon double bond makes an alcohol. Hydrogenation of a carbon-oxygen double bond creates an alcohol. How do alcohols react? Yeah, we're going to go into this and we're going to go into oxidation. There's going to be oxidizing agents like this. That's potassium dichromate, potassium permanganate. We will use this symbol. And when you see this, when you see an arrow with brackets with an O in the brackets above it, we're saying, okay, what would be the oxidation? We're signifying the oxidation of that molecule. All right, now let's do a little bit of review here. And kind of go from 1305, where you talked about oxidation reduction reactions. Let's talk about oxidation in this organic chemistry context. They are consistent with one another, but we define it a little bit differently. You remember in 1305, we focused in on electrons. Oxidation is the loss of electrons. Reduction is the gain of electrons. And we kind of followed the electrons. In organic chemistry, we're going to follow the oxygens and the hydrogens. And we're saying, we're defining oxidation as the gaining of oxygen or the loss of hydrogen. Usually 2 hydrogens. And just like in 1305, reduction is the opposite of oxidation. It's the exact opposite. Reduction is the loss of oxygen or the gaining of hydrogen. Okay? Now this slide, I bring this slide up, you're going to see this slide in every chapter now. Chapter 12, you're going to see it in chapter 13, you're going to see it again in chapter 14, because in chapter 13 we're going to talk about these molecules. In chapter 14 we're going to talk about these molecules. And I'm going to keep bringing this up, so you might as well get used to it right now. Make friends with it right now. All right? So let me introduce you to it. What we got here, here's an alkane. You're familiar with that, chapter 10. Here's an alcohol. What has happened? This has an oxygen. This doesn't. All right? So this alcohol, when you compare it to this, has gained oxygen. Yes? Right? So it did what? It oxidized. Now let's compare this alcohol to this aldehyde. What happened here? What's the difference between this and this? It lost hydrogen. How many? 2. I'm sure glad it wasn't 55. All right, it lost 2 hydrogens and formed this double bond. So it is what? It is more oxidized than this molecule, and even much more oxidized than that one. All right, as we move along here, the molecule, the organic molecule, is becoming more and more oxidized. So when we compare the aldehyde to this is carboxylic acid. Like I said, you'll become real good friends with those in chapter 14. What has happened here? It gained an oxygen right there. So it did what? Oxidized further. That's what we're saying right here. As we move from alkanes to alcohol to aldehydes to carboxylic acids, the molecule is becoming more and more oxidized. All right, and then if you were to start with a carboxylic acid and move back here, you would see the exact opposite happening. It's losing oxygen, it's losing, what is it doing?
Oxygen.
Losing oxygen, it's gaining hydrogen, and losing oxygen. That's all reduction. Okay. Okay, so keep that in mind, because now we're gonna oxidize an alcohol. We're gonna oxidize an alcohol. You're gonna see things like this popping up as it undergoes oxidation. So here's this is 1-propanol, a primary alcohol. Okay, now let me try to concentrate on this one, because I'll tell you this. This is the most complicated. Secondary is less complicated, and tertiary is easy. All right? What we need to understand right now is that each class of alcohol oxidizes differently. All right? So you need to be able to parse out what kind of alcohol is this and what's it going to do when it oxidizes. This is what primary alcohols do when they oxidize, or they can do. Don't worry about this for right now. Let's go up this high road for a second, because we've got 2 reactions on here. We take this 1-propanol. We can take a mild oxidizing agent like that, chromate, mild, and oxidize it to an aldehyde. There's an aldehyde. Or we can take a strong oxidizing agent and oxidize it to a carboxylic acid. On the chart, on the previous slide, and I think I'll go back to that. Remember, it was alcohol, aldehyde, carboxylic acid. That was the order of oxidation. So this is a more oxidized product than that one. It's actually kind of hard. It's not very easy to make a aldehyde out of a alcohol because you have to keep it cool. If you are too rough with it, it goes all the way. It's kind of like you start a rock going down the hill and it's kind of hard to stop it until it gets to the bottom of the hill. See, so we're going from the alcohol into the aldehyde to the carboxylic acid. And that's what a primary alcohol can do. So you can go here and form the aldehyde. You could oxidize it further. If I put the O right here, and or heat it up a little bit or whatever, you could push this right on through to here. So you can get there this way or you can get there this way. But you are getting it completely, fully oxidized. Once it's to the carboxylic acid, you can't do anything further with it other than burn it. You could burn it. And it'd form carbon dioxide, which is further oxidized. But you can't take carbon dioxide and convert it back into these organic molecules. You could go back through this route from that molecule. So let's just take an example. Let's take a real simple molecule. This is a primary alcohol, ethanol. And you draw me two molecules. I'm going to label it above here. Show me what you would get if that oxidized to an aldehyde, and show me what you would get if it oxidized to a carboxylic acid. And I know you're not very familiar with these two classes of molecules yet. Maybe that's part of the advantage of looking over all those functionalities in Chapter 10. But look at the slide we have there and pattern yourself after it. Don't worry about what they're called. Don't worry about the name of the molecule, just the structure. I'm not holding you accountable for the names of these aldehydes and carboxylic acids yet. Be sure to count the number of bonds around every carbon, particularly where you put that carbon-oxygen double bond. Pay attention to how many hydrogens would be on that carbon. So this is the primary. Like I told you, this is the hardest one, or the harder one. Good. That's good. 1, 2, 3, 4. Okay? You're all done there. So there is a hydrogen there. And you're done. There's no hydrogen on there. There is a hydrogen there.
So it's 1, 2, 3, 4.
Yeah. Yeah, you count all the bonds around there. Okay. So you should, for the aldehyde, you're going to get something like this. There's the aldehyde. We are removing two hydrogens. So let's say those two hydrogens. Or if you want to leave that one down there, those two hydrogens. And you're ended up with an aldehyde. That's oxidation. And then it can oxidize a little bit further. And you're going to get this. This is a carboxylic acid. It has a carbon-oxygen double bond, and it has a carbon hydroxyl, or an OH bonded to the same carbon. These aren't on two different carbons. Those two things are on the same carbon. That's a carboxylic acid. Okay. Any question? Okay, let's take a look. Like I said, you're over the hardest part. If this were a week, you're at Wednesday, and now you just got Thursday and Friday ahead of you. All right? So let's look at secondary. Here's a secondary. Let's take a peek at this structurally. This is what we have structurally. And it is isopropyl alcohol. That's isopropyl alcohol. And we're going to oxidize it. It is a secondary alcohol. Secondary. What's the situation here? We have an OH on a carbon, but there's a carbon on either side of it. So this can't form an aldehyde. An aldehyde forms a carbon-oxygen double bond on the end. By definition, that's what an aldehyde is. There's no way we can get an aldehyde out of this. What we get is this. And notice here, where we get this carbon-oxygen double bond in the middle of the chain somewhere, there's no hydrogen here. No hydrogen there. We've got 1, 2, 3, 4 bonds around that carbon. So just don't come along there and go boom, boom, just throw lines all the way across there because you got a carbon chain. You've got it satisfied here. And this is a ketone. And the reaction is done. That's all you get. A secondary alcohol produces a ketone. All right, let's take a little. You with me? Everybody with me? Am I going too fast? Let's take a. I'll write the structural formula here. Let's work with this alcohol. Yeah, let's oxidize this alcohol. There's another hydrogen right here. That's cyclohexanol. It is a secondary alcohol, right? We've got an OH, but it's got a carbon on either side of that carbon. So it is a secondary alcohol. Draw the structure, don't draw the line formula, draw the structural formula of the product and show all the hydrogens. I like to see these in the ring, these carbons. See how I have mine in the ring? I don't have them sitting outside the ring. I have them actually in it, like that. That's better than that.
Yeah.
Because this gets a little confusing. Okay. Yeah, that's okay. Okay. So you're probably going to get something like this. and you're going to get a double bond right there. And then you're going to have your hydrogens coming off of there, and that's it for that one. You got 1, 2, 3, 4 bonds there. Yeah, we won't worry about the name. We'll get to it in chapter 13. But that is a ketone. That's a ketone. We got a carbon-oxygen double bond in the middle somewhere. It's got carbons on either side of it. Okay, you ready? Here's the tough one. You ready for the really tough one?
Yeah.
Tertiary. Tertiary alcohols. No reaction. They don't oxidize. Okay? They don't oxidize.
So can we just have a bunch
Zena said she'd like to have more of these kind of reactions. All right, every so often, you got to have a good day. And here's a good one. Okay, so let's summarize. Let me just summarize for a second over here. Primary alcohol oxidizes to an aldehyde, which can further oxidize to a carboxylic acid. So we'll just call it, this is just kind of a summary of the oxidation of alcohols. Secondary alcohol oxidizes to ketone. And a ketone does, in a ketone, I don't know if this would be any better, no reaction. You try to oxidize the ketone, it doesn't react any further. That's where it stops. Tertiary alcohol, oxidation of a tertiary alcohol, no reaction. Nothing happens, okay? So be able to separate these out, distinguish them. On your homework, I give you 3 alcohols. One's a primary, one's a secondary, one's a tertiary. Very first thing you have to do is decide what class of alcohol is this? How does that class of alcohol oxidize? What is that product going to look like? Draw that product. Draw the product of the oxidation. Now, for a primary alcohol, you could draw either the aldehyde or the carboxylic acid. And I would give you credit for that, okay? You'd say, well, it's going to be the aldehyde or the ketone, or the, it's going to be the aldehyde or the carboxylic acid. Well, either one. So you can show me either one or show both or whatever you want to do there, but those are accurate answers to the question, what would you get if you oxidized a primary alcohol? In a secondary alcohol, the accurate answer is it's ketone. So it's got to be a ketone. And the tertiary alcohol is simply, there's nothing. You end up with what you started with, your tertiary alcohol. Okay, now this is the last one for today. The dehydration of alcohols. So far in chapter 10, we learned that halogenation was a substitutionary reaction. The type of reaction was substitution. In chapter 11, we learned that hydrogenation of a double bond was an addition reaction. And now we're going to learn a third type of reaction, elimination. Elimination. The dehydration of an alcohol is an elimination reaction. And we're going to have to learn how to apply a new rule, Zaitsev's rule. I'll come back to this slide. This is far enough introduction for right now. I'll come back to this slide. Let's take a very simple alcohol, ethanol, and the product of this is going to be, there's not going to be any ambiguity. There's only one possible product. But when we talk about elimination, when we talk about dehydration, we're going to produce water. One of the products is going to be water. Where are we getting the water from? Well, we're going to eliminate the water from the molecule. This is why it's an elimination reaction. We've got two hydrogens there and an oxygen, which is H2O. So we're going to eliminate that. And if you think about that, if you think about this bond, and if you think about this bond, just kind of think in reverse of what I've been showing you already. This electron can come down in here, and we get water. We get H2O. Now we form another hydrogen-oxygen bond right here. And that completes our water molecule. What are these electrons going to do? They're going to collapse back into the carbons and make a double bond. Exactly. Zena and I are up here having a conversation. Anyone want? I'm not talking to myself. Okay. I do that at times, but I make sure I'm alone. I try to make sure I'm alone. All right. All right, so you form a double bond. So this is the reverse of the hydration of an alkene to form an alcohol. This is the exact reverse of it. We're dehydrating an alcohol to form an alkene. Beautiful stuff, huh? Pretty neat. Okay, so now let me get to a little more complicated molecule. Before we get to that more complicated molecule, let me tell you that hydrogen doesn't come from just anywhere. This hydrogen, to form that water molecule, has to be on an adjacent carbon. All right? That's the only place that hydrogen can come from. An adjacent carbon. Because then those two carbons is where the double bond forms. So here, let me give you another example, and you'll hopefully will understand what I'm trying to say. Let's take this situation. What situation do I want to take? This situation. Pretty simple molecule right here. But you can see the OH is sitting between two hydrogens. Okay, so what does that mean? Well, that means... Wait a minute. Is this the molecule I want? Yeah. No, let me put another carbon right here. I need to put another carbon over there. I don't need it for its hydrogens. I just need it for this illustration. But you can see that I've got two choices. This OH has two choices. I can leave with this hydrogen to form water. I could leave with that hydrogen and form water. But if we follow that reasoning a little bit, we could see that if we lose that one, we get this molecule, right? And if, I'll put a box around this one, if the water comes out of there, it can't do both. If the water comes out of there, we form this molecule. Are those different? Yes, they're different molecules. This is 2-butene. Cis or trans, we don't know. Right now, we don't know. But this is 2-butene, and this is 1-butene. Those are two different products. All right, so one of these is a major product. This one. And one is the minor product. This one. And where Markovnikov made his name for himself on the hydration of double bonds, carbon carbon double bonds to form alcohols. Zaitsev made his name on the dehydration of alcohols to form the alkenes. And he didn't decide what was going to be major and minor. He empirical. This is what I mean by empirical evidence. He went into the laboratory and dehydrated alcohols, and he analyzed what he got. What am I getting here? What am I getting here? What am I getting here? Oh, it looks like I'm generally getting, the major product is generally this kind of a product. And he came up with Zaitsev's rule. And Zaitsev's rule, we'll go back and read it here in a second, but it said the major product is going to be the carbon-oxygen double bond that has the most carbons attached to it. So this carbon-carbon bond has 2 carbons directly attached to it. This carbon-carbon double bond has only 1. Don't count this out here. Just count the carbons that are directly attached to either one of these 2 carbons. And all we got around here are 3 hydrogens and 1 carbon. And around here we've got 2 hydrogens and we have a carbon on either side of the double bond. So this is has more carbons attached to it. It's the major product. So let's go back and read the rule. The product that gives the highest number of carbons attached to the double bonds is the major product. Zaitsev's rule. Okay? So you really should be pretty conversant with these 2 rules, Zaitsev's rule and Markovnikov's rule, so that you can predict the major products. That's what I will generally be doing, even on tests and things like that. I'll give you a reaction like the dehydration of an alcohol, and I'll say, draw the major product. Okay, so here's the example. Here's 1, 2, 3, 4 carbons. We've got an OH on the second. This is carbon number 1, 2, 3, 4. 2-butanol. It's 3-methyl-2-butanol. We got an OH right here. There is a hydrogen here. There is a hydrogen here. And if it leaves with this hydrogen, we get the double bond here. But the only carbon attached is 1. They got the box around this whole thing, but there's only 1 carbon directly attached to these 2 carbons. That's the minor product. Whereas if this leaves with that hydrogen, you get a double bond right there. Right where the OH and that hydrogen were, you get a double bond. And what do you have? You got 1, 2, 3 carbons around that double bond, making that the major product. Okay, let's look at one more example. I'm going to draw this down here. And there's a hydrogen. Now there's a hydrogen here too. I don't know where to put it. I want to get it out of the way somewhere. There is a hydrogen on this carbon, but we need to look at the hydrogens that are on the carbons next to this hydroxyl. So there's a water, in which case the double bond would come right there, right? There's a water molecule that could leave. You could eliminate this water molecule, in which case you get the double bond right there. That would be the minor product. Why? If you can see with the double bond here, let's look up at that top one. You've got a carbon here, you've got a carbon here, and you've got a carbon here. So there are 3 carbons around the carbon-carbon double bond. The other product get rid of that. The other product with the double bond right here has only 2 carbons around it. This is the minor product. Okay, any questions? All right, I've given you something to think about. If some of this is still soaking in, let it soak in. Come back and look at these slides and look them over again. You know, in the next 4 hours or so, if you can, or as soon as you can before this ends up being a fog that just came over in the morning and is now clearing. Have it settle on you. Okay, now I've got something for you. I'm done with this.